Jean-Louis Leroy. I'm going to talk about open multi-methods. So I'd like to run a quick poll. Who knows what an open multi-method is? One. Okay, good. Okay, so let's go. So 1981. This is probably the dawn of the age of object-oriented programming, with the issue of byte dedicated to Smalltalk. Maybe some of you remember that one. Smalltalk is not the first object-oriented language, of course. The first one was Simula, which was created around 1960. And that's actually the language that invented inheritance, virtual functions, and so on. But it was a language which was dedicated to making simulations. So it didn't really gain much audience beyond the world of simulations. But Simula, which was a sort of derivative of Algol, is actually the main source of inspiration for C++. Simula added object-oriented features on top of Algol, and C++ did the same on top of C. A little while ago, Alan Key and others created another object-oriented language, Smalltalk, which owed nothing to Simula. It was more something like inspired by Lisp, in my opinion. It had closures. It even had church booleans, and it was a dynamic language. And that's, I think, the language which really introduced object-oriented programming into the mainstream. Smalltalk had a very powerful metaphor, which is that you have objects that communicate by sending messages to each other, and each object reacts to a message according to its nature. Well, that's a very good metaphor, because I used to teach C++ and object-oriented programming in C++ and Perl when it was something new. And people, would freak out when they would hear the word polymorphism, big Greek word. And I would tell them it's easy. You kick an animal. If it's a cat, it meow. If it's a dog, it barks. And if it's a pit bull, it bites back. Oh yeah, that's all there is to it. Okay, polymorphism, as simple as that. So it's a very good metaphor, but as we shall see, it's very limiting. Soon afterwards, everybody was adding object-oriented features on top of his language of choice. In my case, it was Forth. That's the language in which I learned to program. Objective-C did it. C++ did it, of course, around 83. Then came Java. But all those languages kept the idea that polymorphism is obtained by sticking virtual functions, methods, whatever you call them, inside a class. Almost all but one, the Common Lisp object system, followed a different path, which I believe was the right path, as I will argue. So it was fresh and new, and object-oriented programming was going to solve all the problems of the world. We were going to get reuse. They even coined that cute word, software ICs. So what is a software IC? It's like an integrated circuit. Oh, you remember the term? So you take it off the shelf, and you take another one from the shelf, and you compose them together, and it's beautiful. You compose them as you need them. We were going to get modularity, maintainability, quality of code. Thanks to that, we were going to solve the software complexity crisis, because back then we had a sort of problem. We were trying to make programs and user interfaces which were more and more complex, and many people were getting a bit lost trying to do it with C and switches and pointer to functions and so on. So object-oriented programming brought some order into all that. Now it's become sort of fashionable to criticize OOP. some of the criticisms are deserved, I would say, but I also believe that OOP is a very useful tool to address the complexity of software development, and I believe it's going to stay. But I'm going to focus on reuse. So, did we get code reuse? Sort of. We got it to an extent. For example, there were application frameworks like Borland, OWL, Microsoft DocView, and so on, which made it easy to quickly build applications that have a file, open, save, menu, and so on. And in the case of those frameworks, it's actually not you who call the code, it's the code that calls you. So you use them by deriving classes from the framework, and you override virtual functions to fill in the blanks, to give your application-specific code, and the framework takes care of the rest. And some of them work quite well. Something else which worked quite well was the toolbox approach. Like, for example, a string class. You use a string, it's been optimized, tested, and so on. So it is actually a good example of a software IC that works, string. But it didn't always work that well, and we're going to see examples. And I think that what went wrong was actually because of that insistence of seeing polymorphism as virtual member functions. So you can take this entire presentation as a rant against member virtual functions. So object-oriented programming is based on 3 pillars: encapsulation, inheritance, and polymorphism. If you don't have polymorphism, it's often called object-based programming. This is a nice picture. The reality is a bit different, in my opinion. It's more like this, because in most languages, polymorphism without inheritance doesn't really make sense. Now there's a new generation of languages that try to separate inheritance from polymorphism, and Go and Rust come to mind. In my opinion, they're not as successful as some believe, but okay, it's interesting. So in C++, we get polymorphism by implementing virtual member functions. And I believe that approach has several big disadvantages. So I'm not going to read these because I have slides about it just now. I'm going to take them one by one. And for that, I'm going to take a small example. A matrix class hierarchy, or a matrix library. So we all know that there are several, beyond the concept of a matrix, there are several important subtypes of matrices. Diagonal matrices, 3 diagonal matrices, symmetric matrices. Huh? Diagonal matrices? Yes, all sorts, right? And that has at least 2 consequences. One is that in the case of a diagonal matrix, you don't really need to store all the zeros. So from a practical point of view, you're going to vary the representation of your matrix depending on the exact subtype. And also, some mathematical operations on matrices can be done much faster. If you take into account, for example, that a diagonal matrix is diagonal. In that case, inverting a matrix is much faster, or transposing a matrix is a no-op. So in our matrix library, we're going to have a matrix abstract base class, and from which we're going to derive an ordinary matrix, which is going to store all the elements. It's the default case. and diagonal matrices, spheres, and so on and so on. So this is, of course, a very simplified example. And we're going to vary the behavior, the algorithms, depending on the exact type, by using virtual functions. So far, so good. So here I have a transpose and an invert virtual functions, member functions, and we implement them in the subclasses. Looks good. Until you realize that's the first problem with virtual member functions. They increase coupling, and it can get very bad. Okay, let's assume that I have application 1. This is main. This is main. This is the library. So application 1 is going to do, everything. It's going to do matrix addition, transposition, inversion, everything. And then we're happy, right? We link with our library, and all the code that is pulled in by the linker is actually used. But it's not necessarily always the case. In this second application, for example, we do matrix transposition, but we don't need to invert matrices. Well, the code for inverting matrices is still pulled in because of the way virtual functions are implemented. When you construct, let's say, an ordinary matrix, one of the things that the constructor does behind your back is to set the pointer to the virtual function table, which is a vector of pointer to the actual implementation of those functions. So the consequence is that the invert function is linked in, even if it's never called. It might be called. I mean, when you compile a library, there's no way to tell beforehand that it's going to be linked with this application that doesn't need matrix inversion. Well, typically you can do many things on matrices. So it's likely that you're going to have a lot of functionality in your matrix class, and you may end up using only a small subset of the code that you pull in from the library. And it can cascade. I'll come back to this example in a moment. So this is problem number 1 with virtual member functions. They increase coupling. So we talked about modularity. Virtual member functions don't make it easy to write really modular code at the physical level. Second problem with virtual member functions. They don't support extension very well. It might be useful to write a matrix to a stream, or to serialize it, or marshal it, whatever. There are many similar situations. So how can you implement that? Because, for example, you may want to write a matrix to a stream using different format depending on its exact type. For example, well, in the case of an ordinary matrix, you simply write all the elements, but in case of a diagonal matrix, maybe you just want to write the diagonal, or maybe you want to write everything after all. In case of serialization, typically before writing the content, you want to write a type ID, so that you can reconstruct an object from the right type when you serialize your objects back in. Here we have, in fact, already a first problem, which is who decides what writing a matrix to a stream, what the output should look like. In my opinion, it's not the matrix business to decide. It's the application's business. But because we need polymorphism, and because in C++ the only way to get it is to use virtual member functions, we may end up writing things like this. So we add one more virtual function in a matrix-based class. We can probably give it a default implementation. and we override it in the subclasses. So first problem, it's the matrix which gets to decide what the output is going to be like. That's not so good. Also, that type of approach may lead to what is called a fat-based class, meaning that a class is going to try, in anticipation of all the things that this developer or that developer may want to do with matrix. Well, I want to be complete, so I'm going to add lots of functions which, again, are not going to be used most of the time. And about decoupling, one more word about this. Once you do things like this, you're going to, if you instantiate an ordinary or a diagonal matrix, or even just a matrix here, because I've provided a default implementation, those functions are going to be linked in, even if they're not used, and in turn they're going to pull in the stream library, which I don't want if, for example, I'm writing code for a controller, a device controller, or for a device. Typically, I want my code to be as compact as possible. So in those contexts, the matrix class is not going to be very usable. Now I'm going to talk about a real life example. This happened in 1997. I was working on the automation of the Belgian appeal court. So Belgium is a complex country. Justice is a complex topic. So we were working on a very, very complex subject because we had all the appeal courts which couldn't agree on the procedures and so on. So the application was, in fact, dynamically configured by objects stored in the database. And from one jurisdiction to the other, the screens actually looked differently. We had to construct them dynamically. One of the architectural decisions in that project was to have a 3-tier architecture with a business layer, below the business layer, persistence layer, and above the business layer, a presentation layer. The business objects were to be put in a library, and beside the main application, we also had a collection of command line applications to be used in batch mode. So that business library was actually going to be reused across several applications. The problem was if the UI at one point pulls an object from the database, it typically doesn't know its exact type. For example, in a criminal case, you can have parties which are natural persons and legal persons. So in your criminal case, you have a vector, a collection of persons. So when the UI displayed a case, it would show a list box containing the parties, and the parties had methods to return a description. It still makes sense to put that in the business layer. But once you clicked on a specific party in that list, you had a part of the screen that displayed the full object. So it was a master detail arrangement. So the problem that criminal case form had, that the dialog had, is that, okay, I have a person. I know that it's either a natural person or legal person, and I want to make a UI element or a dialog box or whatever to display that object to the user when the user selects that object. So, okay, I have a pointer to a person. How do I make either a pointer to a natural person dialog or a pointer to a legal person dialog? It's exactly the same problem as the write function. So There are solutions to that. You can make a type switch. Person P equal retrieve from database. Okay, if dynamic cast P to natural person pointer returns something, then it's a natural person. Create a natural person dialog, and so on and so on and so on. It works well with persons because there are only two types of person: natural person and legal persons. But it doesn't work so well when you have many more classes, and even more if the complete set of derived classes cannot be anticipated. The type switch is not extensible. Then it was the age of design pattern rage back then, so we considered abstract factory. Abstract factory is nice because you can actually decentralize the production of one type of object based on another type of object. The problem with abstract factory is that it doesn't understand inheritance. Sometimes we had to create pieces of a user interface that where we didn't really want to display all the details. Sometimes we were satisfied with just creating a person dialog. Well, rather it was a set of person controls. But so that's the problem with abstract factory. It doesn't know about inheritance. Really, the only thing that knows about inheritance and polymorphism in C++ are again virtual member functions. So it's pretty disgusting. I'm not proud of having done that. But what we did was actually in a business layer, in class person, we added virtual functions which actually belong to the user interface. So we had class dialog, semicolon, and those declarations, and we had a little Perl program that generated stubs for those cases where we wanted to use the business object library in a console application. And in the case of the main graphical user interface, in that case, we provided proper definitions for those functions. So, wow, it's disgusting, right? It creates a cycle. I mean, it works on its head. The business layer is not supposed to know about the presentation layer, of course, but we still did it because it was actually the easiest way, the most practical way of doing things. So, in fact, in this case, it would have been so great to be able to create a virtual function which would live outside of the class person, which would live just inside the business layer. Okay, to clean our mouth from the bitter taste of that example, let's look at an example of a much better design. It's taken from the standard library. In the standard library, we have class string and we have the streams. And the strings are not aware of the existence of the streams. And likewise, the streams are not aware of the existence of the strings. How do you read a line from a stream? Well, you have something which sits above, which is called getLine, which is a free function. It doesn't belong to string because it has no business belonging to string, and it doesn't belong to the streams because it has no business belonging to the streams. This is the right way of making the dependencies. Likewise, operator shift, which writes or reads a string from a stream. It is also something that sits above both components. And it is also a free function. It doesn't belong to any class. And then you have the string streams, iString stream, OString stream, and those, their business is to implement a stream in a string, so it's perfectly logical that they know about both classes. But the point is that a program can perfectly well use string without using streams, and use streams without using strings, and that is good. But the reason why we can have that clean design is that neither string nor ostream or istream, they're not polymorphic. If string was an abstract class which is the base of a hierarchy of string subtypes, and if getLine somehow had to vary its behavior depending on the exact type of the string, we would be forced to stick getLine inside the string class. And if streams were polymorphic, well, we'd have the same problem. We would be forced to stick getLine inside the stream classes. We cannot have both, right? Okay. Also, virtual member functions violate encapsulation. So, every 6 months that debate pops up again. Friend. Does friend violate encapsulation? And some people say, yes, you should never use friend. And some people say, no, it actually helps tightening access to a class by making it possible to not make everything public. And it's funny because the people who spend time debating about whether friend violates encapsulation or not, they don't seem to realize that virtual member functions have exactly the same problem. Actually, it's even worse. If I need to be a virtual function, if I'm a function, I need to select my behavior depending on the exact type of an object. I have no choice. I have to be a member function, and suddenly, I get access to the object's private part. Why? Why? If you look at virtual member functions, often they don't need special access to the private parts. Often they can be written purely in terms of the public or protected interface. So, isn't that strange? In fact, what we get here is something like this. This is object-oriented programming according to C++. We have a sort of magma which sticks together membership, encapsulation, polymorphism, and then we have inheritance. So that is not good. One more thing. Virtual member functions don't support multiple dispatch. If you're going to add two matrices, if both matrices are ordinary, in that case it's easy. You just sum all the elements and you return an ordinary matrix. But if both matrices are diagonal, you really want to select again a specific algorithm for addition, because you're going to just add the two diagonals, no need to add all the zeros. You have a question?
Yeah, the previous comment you made about for member functions have access to the private implementator. Do you mean derived member functions have access to private?
No, not derived, but
arbitrary member functions have access to the encapsulated data.
Yes, because they live inside a class, right?
Okay.
So back to this. Here is a case where you want to select a behavior depending on the dynamic type of two objects. So how do you do it? Well, there are sort of solutions. You can revert to a type switch. If dynamic cast A to diagonal and dynamic cast B to diagonal return something, in that case I know that I have two diagonal matrices and I do something special, and when I want to instantiate an object to contain the result, I instantiate a diagonal matrix instead of an ordinary matrix, and it works, except that again you lose extensibility. one of the promises of object-oriented programming was that you could take a class library, a class hierarchy, and you could add your own classes and everything would keep working, provided you adhere to the Liskov substitution principle. It's supposed to be extensible that way. Except that when you want to do that sort of things, if you do it any time you use a type switch, you're actually hard coding the set of all possibilities. So you can kiss goodbye to extensibility. Another strategy, well, and also type switch are slow because they rely on dynamic cast and so on. An alternative is double dispatch. So you have A, which calls into B, passing it itself, and A knows its exact type, and we do it the other way, and then after two virtual function calls, we know the exact type of both objects, and we can do what's right. Two problems with this. Again, it is not extensible. If a user adds a class to the hierarchy, to make double dispatch work, he will have to go back to the metrics-based class and modify it. Something that maybe he cannot do. Maybe he doesn't have the source code, or maybe he doesn't want to do it for whatever reason. So double dispatch is not a great solution either. Also, I don't know if, sometimes you need to select behavior depending on 3 arguments. At Bloomberg, we have a case. We have quantitative analysts which want to select an algorithm, a pricing algorithm, depending on a pricer, a model, and an asset class, right? In that case, you would need to implement triple dispatch by hand. I don't know if anyone ever attempted this. It looks messy. And it's not maintainable either. Because each time you add a subclass, you have, to chase all those type switches. Okay, now there's visitor too, but visitor suffers from exactly the same problems. Not extensible, complex, not easy to maintain. So, to address all those problems, well, there is something called open methods and open multi-methods. That is actually the approach that Common Lisp took in around 1985, yes?
What do you think about boost variant and multiple visitation? I think it's a good alternative for double dispatch or multi dispatch. Thank you. What do I think of a boost variant as an alternative to double dispatch or multiple dispatch? I haven't really used boost variant. I looked at it, and it. So.
I think I can answer.
Yes, please.
That isn't extensible either, because you have to change the variant type if you want to extend. So it boils down to the type switch or visitor, but in both cases you have to extend the type of the variant.
Okay, other questions? Common Lisp in around 85 had a solution to that, which is simply not to force polymorphism to live in member functions. And well, this is actually where we see that the Smalltalk metaphor of objects talking to each other, this is where it becomes insufficient, because if you say A plus B, who's receiving the plus message? In Smalltalk, you can say 5 plus 3/4. Smalltalk has a fraction type. And because of the way Smalltalk works, the plus message is dispatched to the first argument, taking the second argument as taking the second operand as an argument. And then the two objects engage into a sort of negotiation to decide which one is more general. So, that sort of chit-chat makes Smalltalk really, deserve its name. And basically, yeah.
That metaphor is very limiting. So in 85, the Lisp community tried several different implementations of object-oriented programming. And some of them actually also used the message passing metaphor. But finally, they had something called loops and flavors, and they created the common Lisp object system in which member functions in which polymorphism is not achieved via member functions. So how is it achieved? We're going to see. And in fact, that problem has been identified by Björn Strostrup a long time ago. Around 2006, I think, with two collaborators, he wrote papers and I think even a proposal that suggested the introduction of a new way of doing polymorphism in C++, which looks like this. So let's take it one step at a time. On the left, it's the old way. Okay? I'm taking the example of writing a matrix to a stream again. The new way, using the syntax that Strostrup proposed, is to move right outside of matrix and diagonal. Here we declare a free function. But in front of the matrix argument we say virtual. It means that this is a method whose implementation is going to be selected depending on the type of the matrix. Here we put the code for the general case. How many rows, how many columns, I iterate, I display everything. And here we can create an overrider or specialization. Here we say write or stream virtual diagonal. And it works exactly like the example with member functions, yes?
And how would that be different than just providing pointers or references to a matrix or a diagonal? And just providing a free function with and that takes a... You pass it by base class.
Okay, repeat. How would that be different from creating a...
Passing in matrix objects and then specializing the function for diagonal objects. How do you know?
Yes.
Boom, thank you. Thank you.
You do it by implementing multi-methods. Okay, next.
So now it seems like you have the opposite problem. Now how does the compiler know to link that each of those virtuals in to the program when it can't? How does it know that it needs those?
Okay, so now how does the linker know that it needs to link in the right specialization, right? I have the opposite problem, that's what you said, right? Yes, indeed. Well, that's a good question. Strostrup doesn't talk about it. My take on this question would be this. We would need an extra step during the link phase. The problem is not so much the base function, right? If we call write here, if any part of a main calls write, then we want to link this one in. But how do we know that we need to link in the diagonal specialization? I think that it's simply a matter of looking at all the objects files and see if they instantiate a diagonal. It's a matter of finding the calls to the constructor of diagonal. If we find a call to the constructor, it means that our program contains diagonal matrices, so we need to link the specialization in. Okay?
Maybe. I have to think about that.
Yes, of course.
The call to the constructor could be buried in an SO somewhere that you don't see. And you could get a shared pointer to it back, for instance, from the shared object that you're linking to, so you can't rely on it.
Okay, so the call to the constructor could be hidden in a shared object that possibly you link dynamically.
Yes.
Yeah, but this is a different context. When you do static linking, you get a self-contained executable, and you want it to contain only what you use. If you make a shared object like, I don't know, the GCC library, you want everything to be there because you don't know if tomorrow someone will need the things that are not needed now.
I would suspect that the linker would export the symbols. You generate a set of details or whatever to make the lookup.
I mean, the paper explores it.
And by the way, my library support on Linux. It supports dynamically loading shared object via DLOpen. But of course, then there's an extra step which has to be performed. More questions?
So in this, in the new way,
Yes.
what if I don't write the first write function? I mean, it's not enforced.
Okay, in the new way, what if I don't write the first function? Let's call it the base function, right? Well, in that case, if you try to call write on a matrix, you get a compile time error.
If it is a pointer, I mean, if it's a base pointer,
Yeah, but this introduces a function that can be called on matrices and the subclasses. So if you don't introduce this one, then you get a compile time error. And it doesn't matter if you use a pointer or reference. By the way, in Strausrup paper, you cannot have a pure method. This one has got to have an implementation. In my library, it's not necessary to give one. In that case, you will get a runtime error. More questions on this? This is probably the most important slide. Yes?
So I actually wrote an implementation and a proposal in 2005 for multi-methods. I think Strausrup proposed his syntax in Design Evolution a few years before that.
Yeah, so Strausrup proposed this syntax a few years before
2005.
Before 2005. Yes, I think so. There are several papers. There's Open Multimethods for C++, Design and Evolution of Open Multimethods, and I think that there's also a proposal. Yeah.
And the one I did, things were registered at runtime, so you could register functions to kind of overcome the shared line problem. So then the data structure was populated at runtime.
Okay, so you could take this model and for example, specialize this function via a closure. You could imagine that you have an open multi-method API that allows you to do that sort of thing. From the papers I've read, it doesn't work that way. It's really, you know, at the syntactic level, it's really close to the old syntax. Now, what is true is that this is actually easier to implement because you know the size of the virtual function table. Here, it's more difficult because when you look at the object files separately, okay, this one may live in matrix.o. This one may live in diagonal.o. When do you know exactly what the set of specializations is? You know it only at link time or when you load a dynamic library. In the case of my implementation, you have to call an initialize function which is going to calculate dynamically the data structure which I needed. If I have time, I'll show you those data structures. But the Strausrup, okay, and let's do them justice. The papers by Pirkelbauer, Solodkey, and Strausrup
mentioned the topic of dynamic loading without giving a solution. I have my solution, and I suspect that the C++ runtime would have to do something once a dynamic library is loaded or unloaded, by the way. More questions? Yes?
So, it seems to me, at least part of your rationale for saying that this is superior is because now the right functions can be declared in the applications, and one application may have a different definition for the virtual diagonal than a different application. Solves a couple of problems you mentioned on the earlier slide.
Yes.
Right.
So the question is, I claim that this is superior because it allows me to add virtual functions afterwards. Yes, that is exactly the point. The problem with virtual member functions is that you can tune existing behavior by deriving and overriding, but you cannot add behavior in presence of polymorphism. This makes it possible. We probably agree that write has no business being in a matrix library, because sometimes it's going to be this and sometimes it's going to be that we want. So this gives you true extensibility. Without this, your extensibility is limited to a cone, which is rooted in some base class. This makes it possible to escape from that cone. Yes?
Does this work with the pure virtual functions, or is it not? Is it like a pure interface? Let's say matrix was a pure interface.
Okay. If
I want to write the right function as pure virtual.
Okay, so the question is, what if matrix is a pure interface? Well, in ThroScript implementation and in ThroScript proposal, this has got to have an implementation. There are no pure open methods. So in that case, if it gets a pure matrix, it could either throw an exception, I guess, or it could call virtual functions inside matrix to achieve, like, for example, in my design, probably get the number of columns, or get an element are probably going to be virtual functions. So I'm not saying that virtual member functions have no reason to be anymore. I'm just saying that most of the time you shouldn't use them.
I was going with a follow-up question because, in a place matrix, I'm thinking of vehicle, a car, or an animal, something can bark and something can, you're giving an example of implementation of a hierarchy. The current method makes it, if I'm implementing a vehicle, let's say a vehicle is drivable, I would like to see conceptually the drive method to be part of the hierarchy of the class rather than outside. If I'm giving an example of a vehicle hierarchy.
So we would have a vehicle class.
Vehicle class and a car or something, and
yes,
these are drivable. Or an animal example you gave earlier.
Yes.
Dog can bark and something else. So, as an interface, if I want to see a matrix, whatever method that it exposes, it's inherent to the matrix, is what I'm looking at.
True, but I think the point is, write is not something that's inherent to the matrix. It's some extra thing you do on the outside.
Yeah, I like the UI example better because that's a more clear separation. I really don't want the UI stuff to be in my matrix.
Yeah.
Exactly.
And also, if you can call a pure virtual function today, and you throw an exception, so it would be similar to that.
Yes.
Yeah.
Now, there have been studies, people who study, academics who study the topic of multi-method have found out that in most cases, single dispatch is enough. In most cases, you would only have one single virtual argument. Multi-method is cool, right? But But this is, in my opinion, in open multi-method, the important word is open. Because now you can add polymorphic behavior all you want without being limited to what already exists inside a class. So even if you don't need multiple dispatch, this is actually 85% of the importance of open multi-methods. Cases like this. More questions? And in those cases where you do need multiple dispatch, it becomes so easy. I haven't wasted time, writing ugly substitutes in current C++. But if you want to implement addition, you simply say something like shared PTR matrix add virtual matrix A, virtual matrix B, general algorithm. And here you specialize for the case where both are diagonals. Goodbye type switch, goodbye visitor. And again, from the outside, you can add more classes to the matrix library. You can add more methods. And all those will it will be possible to combine them naturally. Okay? Questions about this one? Okay. Have half an hour left. Okay, so I've used and I've implemented multi-methods in languages like Perl back in 2000. It so happened that in 2013, Bloomberg invited Björn Strostrup to give a series of talks of his choice, and I attended them, and one of them was about open multi-methods, and he sounded, afterwards I went to talk with him and said, yeah, I find them very useful, I've used them before, and he seemed, a bit dispirited. It looks like he's trying to convince the people in the committee that they're useful, but it sounds as if he's not getting much success convincing them. So I know that it's one of the things he'd like to see in the language, but I don't think it's going to happen anytime soon. So this sort of revived my interest for multi-methods, and I realized that with C++11, finally it was possible to implement multi-methods as a library with a nice syntax and with good performance, provided that you can make some compromises. Actually, the point of Strostrup's talk was the opposite of this library, because his point was that to implement multi-methods efficiently, you need to do it in a language. You cannot do it in a library. And of course, he's right, but as I will show, it's possible to get quite close. My work is of course greatly inspired by the papers by Picklebauer, Solodky, and Strostrup. Also by an old paper which dates back to 1996 about optimizing multi-method dispatch using compressed dispatch tables. Because as we shall see, implementing multiple dispatches has some problems. So in my implementation, we get a fairly nice syntax thanks to the new C++11 features. One of the design goals is to make them fast, close to normal virtual function calls. So inside, multi-methods use tables of pointer to functions, and it tries to make them compact. I'll quickly go over, well, this is just an alternate syntax. How do you use YOM11? That's the name of the library. There are two modes. There's an intrusive mode that I recommend, and which gives you the best possible speed. And there's a non-intrusive mode. If you use the intrusive mode, you have to change your classes so that they give some help to the library. class is simply part of a metaclass system. It it tells the system what are the base classes of metrics and so on. In this case, there's none. It also declares a pointer to data structures that are going to be used during dispatch. init initializes that pointer and should be called in every constructor. I know it's burdensome. So in this example, I simply add those two calls. I'm going to use a shared pointer to matrix as a cheap matrix handle. If I have derived classes, in that case, I simply need to add, after the class name, I add the list of base classes. Yes, question?
A comment. Why couldn't you just inherit from something and you wouldn't have to change it from constructor, but it automatically
Actually,
as a constructor?
so why can't I inherit from something that would
That would implement your pointer redirection, which is probably
that would implement the pointer redirection?
whatever the necessary mechanism for hoisting
Like a CRTP thing?
Well, because when a diagonal matrix is constructed, okay, I forgot to mention something, by the way. There is a base class here which is called selector. I'm working on a new implementation that will rid us of that public selector. So that pointer actually, I think it lives inside selector. But so when you construct a diagonal matrix, first it's a matrix, right? And at that point, the pointer to the virtual function table or the pointer to the multi-method table has got to account for the fact that it's a matrix. And then, a little bit afterwards, it becomes a diagonal matrix. And that pointer has got to change. And I see no way of making this work except by controlling it in a constructor, yes?
How well does this work with inheriting constructors?
With inheriting constructors, that's a good question. I haven't explored that. But I think that you may end up making extra calls to init, but it wouldn't. I don't think it would be harmful.
I think your init is going to initialize it as if it were the base class rather than the new derived class. I don't think it's going to work in those cases.
Well, I'll look into it. Oh, sorry, I didn't repeat the question. How would it work with inheriting constructors? Other questions?
That's why you would need a language feature.
Yeah, possibly. No, I haven't used all of C++11 yet. Maybe you have. Other questions? 30 minutes, okay, good. Okay, derived class, I talked about this. And now, let's declare a few methods. To declare a method, you use the macro multi-method. You give the function name, the method name. From now on, I won't say open multi-method anymore. I'll just call them methods, okay? Question?
More of a comment, I guess. Like the previous question about whether you could inherit from something and then make that work. I think the reason that you can't is because if you inherit from something of his library, your type isn't your type until his library constructor is finished. So his constructor doesn't know what type is inheriting from it.
Even if you use the
curiously recurring template pattern, CRTP, the object isn't of that type until the base class constructor completes, and then you're in the derived class constructor.
Depends on what.
It seems like something that probably would matter.
So you give a multi-method takes the method name, the return type, and a list of arguments. and you mark the virtual arguments by wrapping them in a virtual underscore template. Now there's no limitation on how many virtual arguments you can have. Well, there's got to be one, otherwise it's not a method anymore, but beyond that it can be 1, 2, 3, whatever you want, and you can freely mix virtual and non-virtual arguments, pretty much like what you can do using the Strauss-Script syntax. There are some limitations. In my implementation, the virtual arguments have to be either reference or const reference. In my opinion, it doesn't really make sense to pass a pointer, because a pointer can be null. Well, it's a matter of taste, I guess. Unfortunately, I haven't found a way of supporting overloading. So you cannot have two add methods which have completely unrelated signatures. But one workaround is to wrap them in an inline function, inline, not inine. So here I create an operator plus that simply returns, it calls add. I create a shift operator that calls write. It's okay? Now, how do we define specializations? With, again, macros, begin specialization, give the function name, the return type, and the list of arguments. Here, no need to put the virtual wrapper. Yes?
I just make sure I understand. You declare the multi-method first, and then you declare each specialization.
Yes. Yes. So these typically go in header files.
Right.
And what this does, it simply declares a const add, which is of a type that has an operator function call with this argument list, except that the virtual markers are removed from the argument list. You know, it does some template metaprogramming to remove the virtual specifiers. But essentially, what this creates is something like a const, some very complex type, add. Specializations have to be declared separately, even for the more general case. So here, I create a specialization that takes 2 matrices, that's the general case. Specialization that takes 2 diagonals. So obviously here there are some casting which goes on behind the scenes. Yom 11 tries to use the best possible cast. So in this case, it will see that you can static cast from matrix to diagonal. Because the call is going to be made in terms of the signature of the multi-method. That is one of the differences with the Strauss-Script papers, by the way. The specializations are not visible at compile time. But if one of the base classes, if one of the classes in the declaration here is inherited virtually, in that case, the library will resort on a dynamic cast. Okay, questions about this one? Also, there's a special symbol which is available inside the specialization. It's called next. So what next does, it calls the next most specialized method. I'll explain in a moment what specialized is. Next. So when you override a virtual function, typically you also want to call the inherited function, because you want to add functionality, not subtract it, right? So you use the scope syntax to call the base class. In the world of multi-methods, you call something you call the next function, passing it the same arguments. And finally, this is an example of calling a method. So before using the library or after loading or unloading a shared object, you have to call initialize. This is what is going to reconstruct all the data structures to take into account all the class declarations on one hand and all the specializations on the other hand. So here I create an ordinary matrix which I assign to any matrix. Remember, it's a shared pointer to a matrix. In effect, by doing this, I erase the types. At this point, M1 and M2 are pointers to matrices. We have erased the exact type, ordinary and diagonal. And here I call add, and the algorithm is going to be selected dynamically. And I display my matrix, and it says ordinary and list the content. If I do it with two diagonal matrices, I can see that the addition is a diagonal matrix. So maybe you haven't seen this. In my specializations of write, I prefix the matrix with its type. So that's why it says ordinary diagonal. Questions? Yes?
So when you call next,
yes?
that's not necessarily going to be unique when you have multi-methods.
Indeed. And in fact, yes?
What happens?
Okay, when I call next, it's not necessarily going to be unique. In fact, when I call the method, it's not necessarily going to be unique either. So now it's time to explain. I won't have the time to go through all the slides, but so we understand what it means to use the best specializations in presence of only one virtual argument, right? It's like virtual functions. But what if there are several than one? Now, I could give you 3 or 4 very long sentences that explain the rule, but I don't need to because you already know it. It works exactly like overload, like function overload resolution. Exactly the same way. So it means that you can make a set of foo functions which take 2 arguments, and if you're not careful, you can create ambiguities. And if you try to call it, it will be reported at compile time. In this case, it will be reported at runtime. Yes, more questions?
So the reason I was pointing at next rather than the original thing is that if you're looking at the base call, you can disambiguate with providing another overload. You can't do something like that with next, though, because you're explicitly saying, I don't want to call the most specialized one already in.
There is a macro for calling a specific specialization.
Okay.
But it's exactly like, C is derived from B, B is derived from A, and in a specialization of a virtual function in C, you say, oh, I call A foo.
Yes, but with single...
You shouldn't do it normally. Yes, it's unique, but if you have ambiguities when you call next, it's likely that you should redesign your set of specializations. But there is a syntax to do it, but try not to use it, okay? More questions? Okay. So I'm going to give you a few ideas of how it works. I'm going to use another example because if I use the matrix example, the dispatch tables won't be very interesting. So here's another example where we have a role hierarchy. So you can be an employee in a company, you can be an executive, which is a sort of employee, and you can be the owner, which is not an employee because it owns the whole thing. And another hierarchy of expenses. So let's say that you go on a business trip, you're going to spend money on plane, on cab, or public transportation, either subway or bus. And here we have 2 functions, 2 methods. A pay method which takes a role, either employee or any class derived from employee, and calculates the paycheck. For an employee, it's just a salary. For an executive, he gets a bonus too, maybe. And then there's an approve method which takes two virtual arguments and which basically returns a boolean saying whether an employee can travel by plane. No, he may not. And that an owner, the owner, he's the owner, so he can travel by plane, do whatever he wants. So we have a method here, approve, and a set of 4 specializations. The general case is to say no. And then we give a few exceptions. Employees can take public transportation. Note that here this is an abstract base class. Executives can take the taxi, and the owner can do whatever he wants. So now I'm going to skip this. How can you implement that in an efficient fashion? Well, the fastest way is to use a dispatch table like this. It's a two-dimensional table which contains pointers to functions which are the specialization which is appropriate for each case. And again, for each pair of arguments, we apply the same rules as a function overload resolution. If we find a unique best specialization, we use it. Otherwise, I don't have the case here, but otherwise, it throws an exception. Now, if you look at this table, it's already quite big. Yeah? It's a 4 by 1, 2, 3, 4, 5. It's a 4 by 6 table. So meaning that we have 24 pointers inside that table. And sadly, we noticed that there are some redundancies. The public, bus, and metro columns are exactly the same. And this can be expected because when we declare our specializations, we decide to treat all forms of public transportation the same way. So it's something that is likely to happen when you have fairly big hierarchies. Typically, you're not going to write a specialization for each tuple of arguments. But the consequence is that you're going to have a dispatch table which is full of duplicate columns and rows. So this is the naive way of implementing methods via dispatch tables, but YOM 11 is smarter than that, thanks to that paper written by those French guys in around '96. It groups the rows and columns it merges them to give you a smaller table. What it does, it detects that the same methods are going to be, the same specializations are going to be called if it's public, bus, or metro. Let's look at how a call is dispatched. That was actually one of the more obscure points of Strossow's paper, trying to make sense of a single call. I'm going to try to make it a tad clearer. Okay, let's say that we want to call approve, and we pass it to objects. And it so happens that the first argument is an executive, and the second argument is plain, right? So the way it works. A method has an index which is associated to it. Okay, 15 minutes. Okay. First, note that the problem that we have is that we have an object. We have a way of finding its class thanks to the class and init calls. And we want to turn that class into an index in one of the dimensions of the table, right? We want to do it for the role, we want to do it for the expense. Now the problem is that employee, for example, is going to be row 1 for method approve, but it's row 0 for method pay. So it means that you cannot associate a unique index to a class. It depends on which method you're looking at. So one of the things that a method contains is an index. So here the method approve has 2 arguments and classes contain not one index, I've explained it's impossible, but a vector of indexes. 1 per multi-method. So here approve for its first argument is going to use this column for role, this column. Also for its second argument it's also going to use the first entry in the vector of indexes which are accessed via the pointer which is stored in the object. Pay, on the other hand, is going to use the second index. Okay, so if we call approve with an executive and a plain, first thing it does is to look up the method's index, 0. Because it's extracted from the executive object, it extracted a pointer to this row, it uses element 0 because it's method 0. So we have 2. We get 2. 2 is the index, is the row number in the dispatch table. We do the same for the second argument, plain. Again, for the second argument, we use the first position in the vector of indexes. Here, plain, element 0, so it gives us 3. 3 is the column number, 0, 1, 2, 3. So here, at this point, we know that we want to fetch element. We want to fetch a function pointer in the second row, third column. Remains a little problem. We have to linearize that 2-dimensional address, and for this we use an extra table which is also stored inside the method, which makes it fast to compute the linear displacement in this vector corresponding to position 2, 3. So what we do here, we call approve position 2, 3, which is the same as 2 here, multiplied by 1. It's obviously an operation we don't make, plus 3 times 4 here. There's a small optimization. In fact, in this table, instead of storing a displacement for the first argument, we store directly a pointer to the corresponding entry in the table. Also an optimization which is described in Strauss-Hurst's papers. So this is how it works. I measure the performance of those calls. So I'm going to be honest, this is the best I've ever obtained. Sometimes I got worse results. Of course, it all boils down to your compiler's obedience. The function call operator is marked as inline. It uses a lot of templates, meta programming here. Oh, I shouldn't have done that. Okay, well. Ah, what? Okay, right. The operator function call on the pay method or on the approve method if it's completely inlined, it simply compiles a series of fetch, multiply, add, and so on. The Visual C++ compiler 2013 will inline for one virtual argument. GCC will inline it at least for two. So in that case, here I compare a normal virtual function call with an empty body with an open method call with the intrusive syntax. In this case, I measured a decrease in performance of 33%. So it means that for an open method with one argument using the intrusive mode comes very close to the performance of a virtual function call. But again, it depends on the compiler you're using, okay? The foreign mode, in which you don't need to modify your classes, has to extract the type ID of the argument and use it to find the pointer to the index table. So of course it takes more time. It goes through an ordered map. In that case, of course, it's much slower. To try to make things look a bit better, I added some code to the body of the functions. I calculate a meaningless mathematical expression, and in this case, we see that even in the case of the non-intrusive mode, we get good performance. But how honest is this? I'm not too sure. Okay. With two arguments, this gets interesting too. I timed a two-argument call with using double dispatch and an empty body. In that case, I get 250 nanoseconds, I think. Using a YOM11 method with two arguments and in intrusive mode, I beat the double dispatch by 40%. Okay, questions? Oh no, conclusions. Okay, no, conclusions. Virtual member functions are bad. They're really, really a bad idea. I wish that they had never existed. I wish that one day, 5 minutes, good. I wish that one day they get deprecated. Yeah, that is ambitious, right? But the common list object system never had them, and it's a very good object system. In my opinion, they should be used when C++ supports open multi-methods. I think that you should limit the use of the old-style virtual function only to the cases where you need both polymorphism and access to private parts, which is, I believe, very infrequent. Open multi-methods are a natural extension of C++. It just follows exactly the same rules as function overloading and partial template specialization, except that it happens at runtime. So I hope that we'll get them in a language. It's not going to happen for C++ 17. Or when's the next one? Yeah, exactly. It may never happen. So in the meantime, you can use this library to experiment with multi-methods, and it seems that it's actually used in real projects. At Bloomberg, we have a team which is probably going to use them. I gave you the example of the pricer model and asset class. Questions? Yes?
So I'm wondering, your non-intrusive implementation, if you use that with
So can I use this with Boost Any?
Since
I haven't used Boost Any a lot either, but I also have the impression that it's compile time mechanisms and which don't have the extensibility that this gives.
Boost Any, you can stick any type into it.
Yes.
And you wouldn't have any kind of specialization type issues because there's no inheritance involved.
If there's no inheritance, how can you have polymorphism?
You can stick any type into
Yes.
it, and you can ask what type it holds.
Yes.
And you can get back a type, the object from it, if you know its type.
I'm not sure what Boost Any brings you here, because Boost Any is to copy by value any type, and as long as you know what type to pull back out again, you can pull the value out. So it's if you're not making copies, I don't see the benefit that Boost Any is bringing you. You need to know the type that's in there to pull it out, whereas the whole point of the multi-method is to query what the type is. I can't then just generate, I've got to have all the code for all the different versions there in line,
Right.
in the old classic type switch style.
The idea is that you have your multi-method, which then you ask Boost Any what type it is, match it up against.
Yeah, you have to ask. You have to do the work yourself.
You know what the type ID corresponds to.
Right. So
It's as if you suggested to replace ordinary virtual functions with type switch. You could use Boost Any to replace virtual function, except that your program would have to do the dispatch mechanism.
Well, it's just that your non-intrusive implementation, I would think, as far as I can understand, Boost Any provides what you would need in principle to make it work.
I don't think so.
Really?
I think you would. I think if you have a complete list of all functions in your program, and you've got some Boost Any parameters, what's to stop you looking up those types if you've got no?
But you want to hold a reference to your thing, not a copy of it. It's almost in any reference type rather than
Who cares whether it's a reference or not? That's
well, that's vital when you're trying to do dynamic dispatch and polymorphism.
right.
I don't want to be doing slicing things. I need to get, okay, you're saying you're taking a deep copy of the whole thing, but why am I making copies when the whole point of my function is to say I've got a reference to this, reference to that, reference to the other, and I now dispatch to the most appropriate references.
Dispatching is orthogonal to memory management and making copies.
Yeah.
But Any is all about making copies. It's the whole purpose of Any. It makes a copy without me having, it type erases the type, so I can make transparently make a deep copy of whatever was held in
Okay,
there.
maybe we can continue the discussion because
Yeah, sorry.
take more you had a question?
I've forgotten now.
Oh, good. So next. Who has a question?
I was just going to continue the Any argument.
Oh well, okay. Well, we can continue it at the bar, right? So are there any more questions?
I am curious what that article was that fast dispatch. I just want to get back to that at some point, but I can come up later. Sorry.
Yeah, I'm going to give the slides to the organizers and links. Okay, there are links to that material. YOM 11 is available on GitHub. It has some documentation, and I wrote 3 articles about it so far on Code Project, which explain Yes, you remembered it?
It's not so much a question as an observation that if you think this stuff is cool and you would really like to see this in the future C++11, I don't think Gianna is pursuing personally his proposal. I think it was a pretty good proposal, and if somebody else wants to pick it up and run with it, we would appreciate the manpower.
Yes.
I'm not qualified to pursue that proposal myself.
I picked it up and ran with it in 2005.
That was a different proposal. It was a similar space, but
Yeah, same stuff. But yeah, it was very hard. I did the best when you got to 5.2.
I wish that this becomes obsolete, that my library becomes obsolete as quickly as possible. Unfortunately, it won't be quick, I'm afraid. More questions? Okay, then I have one.
That's not how it works.
Did I convince anyone? Or at least planted a seed of doubt?
Yeah.
Oh, yeah, well, thank you, and thank you to all for coming and listening.